In this video, we're once again visiting volumes by revolution. In this example, it's determine the volume of the solid obtained by rotating the region y equals x squared minus 4x plus 5, x equals 1, x equals 4 in the x-axis, specifically rotated about the x-axis. In which case, what we're going to do is we're going to go ahead and start by graphing all those functions. Now, if you take your time to actually graph these, you'll notice that this parabola right here is going to look something like this. Okay? Next thing I'm going to go ahead and detail is x equals 1, which is about here, x equals 4, which is about here, and the x-axis. Now keep in mind that every time I graph these functions, the idea is I need to make sure that the space that I'm looking at is completely bounded by all 4 of those graphs. So a space that appears to be bounded by at least 3 of them is not going to be enough. Also, it has to be bounded. So you'll notice right here, I have it completely bounded by all 4 equations. Okay, so the x-axis, x equals 4, x equals 1, and that quadratic. Next thing I'm going to do is I'm going to take this region, I'm going to redraw it. Now I'm going to go ahead and draw vertical lines through this. Again, depending on the way we want to cut this, will change how I'm going to draw these lines. But this time I know I'm going to cut it in terms of x. And it's specifically because if I were to redraw this equation over here, again we have something that looks like this. I want to take that object and I want to rotate it around the x-axis. Meaning I'm going to go ahead and mirror image it over the x-axis to the best of my ability. And then I'm going to go ahead and draw those circular cross-sections connecting one piece to the other. Again, they should be circular cross-sections because of the fact that it's rotated around like that. Okay. So now what it looks like is I've got this solid cone-shaped object, but it's got, again, inverted end. So it's a can maybe that was pushed in the center, that has a curve in the center like that. In this case, I'm going to go ahead and try and find the volume of this object. Now, once again, in the last video, we discussed that the volume of an object is x equals, if we're cutting this in terms of x, of an area formula. Well, note again that my region over here starts at x equals 1, that's this location right here, and it ends at x equals 4, that's this location right here. Knowing that where this thing starts and ends will tell me that my bounds are from 1 to 4. Okay, so again, I'm slicing this thing vertically like this, and it makes sense that I'm slicing this thing vertically because if I try to slice it vertically, that will provide me those, again, circular cross sections like this. Okay. So now we also know that my area formula for any disk method is going to be pi r squared. And we just got to figure out what r is. Well, you'll note right here that if I go ahead and try and draw in one of my radius of one of these circles that are in here, the radius ends up becoming the distance from the x-axis to this curve. So I'm going to return to this graph over here, and you'll notice that this distance right here is r. That is going to be r, which means that that distance right there is nothing more than just y. The y that correlates with this quadratic, y equals x squared minus 4x plus 5. So the setup for this integral is going to be simply the integral from x equals 1 to 4, because that's where my bounds on the region start. They start at 1 and they end at 4, if I'm cutting this thing vertically in that form. The area formula for these cross sections are going to be pi r squared in respect to x. But remember, our r is simply the distance from the x-axis to that function. From the distance from the x-axis to that function is y that correlates with this quadratic. So my r is simply x squared minus 4x plus 5. So to solve this integral, okay, what we're going to have to do is actually multiply this thing out. And I'll go ahead and at least set it up so that it's clear what you're going to have, and then I'll let you guys finish the integral on your own. So I'm going to go ahead and multiply out x squared minus 4x plus 5 times x squared minus 4x plus 5, providing me with, looks like x to the 4th minus 4x cubed plus 5x squared. Again, that's me distributing this x squared to all 3 pieces. Then I'm going to distribute this negative 4x to all 3 pieces, giving me a, looks like, negative 4x cubed plus 16x minus 20x, and then I'll distribute the 5 in its finality. So I'm going to go ahead and have positive 5x squared minus 20x, and then plus 25. When I add all these together, and you'll notice how when I wrote these out, I wrote them out in scaffolded so that I have x to the 4th minus 8x cubed. I can simply combine all the like terms. There's 10, it looks like 26x squared, minus 40x, and then plus 25. So this right here is the function that is going to go back into that integral. So I have, in the end, pi integral from x equals 1 to 4 of x to the 4th minus 8x cubed plus 26x squared minus 40x plus 25 dx. And we simply have to integrate that. Plug in the bound of 4 minus plugging in the bound of 1. Again, one more time really quickly, the idea is first step, draw the region. Second step, visualize the object that we're actually trying to find the volume of. Again, the volume is equal to the integral of the area. Every single one of these cross sections, when we do volumes by revolution, should be pi r squared in the first type of examples that we're doing. My r ends up being, based on the way that I cut it, vertical values of y, and that y correlates to the function of this quadratic. Given that I have to do pi r squared for my formula, I have pi, there's my r, which is the function, squared, and I must FOIL that out. Okay. Now, I want to make a note here that the idea is I've set up the integral. This is the conceptual problem. It goes from here to here to here. And after this point, I want you to visualize this example as nothing more than an integral example. How would you integrate something that looks like this? And again, either we would attempt basic integration, algebraic manipulation, or a u-sub. In this case, it requires some algebraic manipulation to get to a function that I can integrate, and then each piece here can integrate. So again, the expectation is that you should be able to do that on your own.